will try is to wrap up a little bit things that we have seen already so that we are back on track. The main goal today will be to understand again once more that one model of understanding why convolution is relevant or so is because translation invariant systems are relevant for applications. And they are actually arising very naturally in nature. If you have a linear mapping, so some procedure which at least locally can be approximated by a linear one, or which satisfies the superposition principle, then you can assume that it is a convolution operator. And there are different ways of modeling it, and one way would be, of course, to take the point of view of a Hilbert space theory, which I think is very important, but I think it's even easier to start with bounded continuous functions. And that's what I did. So I was saying we should maybe take a closer look at the BIBOS system, the bounded input, bounded output systems, from the continuous functions to the continuous functions, but we take the closure of the test functions because whatever we observe is a finite domain, and we want to also observe the output over a finite domain, and anything which is not going into C0 would not be so important. Now, we have seen that you can look at the operators which commute with translation and that the ordinary translations are part of these things. There is a general and very important description that we have studied already. That's the matching between the impulse response of the system, that's what the engineers would do, and the system itself. System is another word for linear operator. So if a black box you put in. Now, as I indicated, there's a problem that I see when you have a system which is a black box, which is linear in a certain range. And if it would be a mechanical system, you mean you apply force to the system. And then you say, well, take a hammer and smash the system. Then you don't know much about the system because it's broken or it's out of the range of linearity. I mean, think of a radio. You turn the radio louder, you will hear louder music. You turn it too loud, you hear not really n times this. So to take a Dirac is maybe not a very good idea. And some people also think that they have to test a Dirac and they take a frequency sweep, which is a Dirac is a sum of all the frequencies, as we'll see in some sense. And so if you don't put all the frequencies into the system at the same time, but with some delay. In the audio domain, we have seen it, I think already, or I can demonstrate it easily. It's a frequency sweep. It's a signal like, and you think it's going up in a linear way. And if it's a short frequency sweep, it's maybe something that the bats are sending out to find out what the echo is doing to orient themselves or so. So these are interesting signals. By the way, the gravitational wave detection very recently, which gave the Nobel Prize, was also detecting somehow a frequency sweep in a lot of noise, and that's where time frequency methods come in. But I'm debating now. I wanted to tell you that we have left out a few little things, or I was making some comments, and that's what I would like to fill in now. I've enlarged the notes, so there are now, so to say, there's the scriptum, the lecture notes, which is really, I try to keep proper, and there are some notes which are kind of a written documentation, a guideline of what I try to explain in the course, and so it's kind of the orientation plan. Now, one thing that we have seen already is that, or which is easy, that we need to approximate measures by discrete measures. I told you that, I mean, today we can turn off the microphone, maybe if it's too loud. My voice is better. We have this discretization operator, which I was comparing with having histograms of a probability distribution with the adjoint operator on the dual space of C0 of something very simple, which is this what I call spline interpolation operator, spline quasi-interpolation operator. So we just recall, if you look at a piecewise linear interpolation or abstractly a spline interpolation operator, then the maximum of the functions occurring will never be larger than the function value itself. Remember, the individual pieces of the definition of unity were supposed to be 0 and 1, and adding up to 1. So you use only a convex linear combination of functional values at any given point, so there can nothing happen. Recall there are maybe some non-negative poo-poos, then you would have a constant here, which would also not be bad. So sometimes it's good to allow non-negativity. For us it's convenient to have this. Now we were using this to say that then the deep psi operator, the adjoint operator, which has the same norm as we have seen. Any operator has an adjoint, or it's a transpose operator. We are talking about Banach spaces here. And it has the same norm. So the discretization operator will have the same norm. But you can try to do it also or see it directly. And I was using this, I was telling you, we have a sum of Dirac measures sitting at these positions psi I, and their amplitudes are the measure psi I. So to say, you have a histogram and take the height of how much you put of a delta. Or you take the distribution function and the jump size is more or less the mass that you have in this region also. So how can you estimate it? And the trick is a harmless trick. You can estimate it, and I can illustrate it very easily by the following picture. Whenever you have a partition of unity, and this is kind of a partition of unity using piece plans, I'm focusing now, I would like to say, if I cut out the, from the measure the blue part, so the part around the blue function. Then what we know already, we can control the sum of the pieces, so the sum of all the blue parts and all the measures multiplied with this blue part. But what we should do, or what I'm looking for, is I would like to apply the measure to the blue function now, which is not the same, of course. So what we do is we take the partition of unity and say, well, mu psi I can be applied to 1. Now 1 is not a constant, therefore we are not allowed to use it. But we can say, well, we take all the things that we need from 1 to reconstitute it. So for every individual piece of the partition of unity, I take all the other ones which are non-zero. And the part of the definition is that finite size, so only finitely many of them overlap. And if I add all the ones which are kind of my neighbors, which have some overlap with this element psi, I was writing psi 15 in my case, and I call the sum over these things psi 15. And you would say, you take a small bound function reproducing that individual atom, and it's an easy way to do it in this way. So if I do it, formally I would take the sum over all the j, or psi j, the neighbors, where they are having non-zero product, and find, of course, there's a typo, that this psi star is a finite sum, and you can reproduce it. You have the property psi I star with psi I is psi I. So you have a plateau function reproducing it. It's just this what you need. And now you say, well, what is the absolute value of mu psi I? I write mu psi I artificially as a product, because then I interchange the order actually and say it's mu psi I applied to this plateau function. Because the plateau function is not larger than this, it's this norm of this local part of this that I can pull out and everything is fine. So we have a control of the absolute value of mu psi I by the norm of the measure localized to psi I. And in particular, of course, then we can say the sum of these absolute values, which was the norm of these discrete measures that we produced by discretization, is at most the sum of all these pieces, and this was exactly the norm of the measure, which was, as I mentioned, the replacement for sigma additivity of measures. So we have another way of understanding that the total height of all these measures is fine. Now, something that will be used on and off, and I have to place it somewhere because I was preparing it. I will do it next. I would like to mention the concept of uniform concentration, and there is a word in the literature called tightness. So we have, the word tight means, when you're English speaking, but means fitting slim. So tight trousers are fitting directly. So it's concentrated. It's not wide and loose. And so if you have a collection of functions, then you would call it a tight family if the concentration is equal or is uniform. Sometimes I also prefer to call it a uniformly tight family. So if you'd give me an individual function, we know in C0, we know it goes to 0. And we have seen you can replace it by saying, well, instead of going to 0, multiplying with a polynomial, with a plateau function is a good approximation, which means if you ignore the values on the plateau, the rest will be small. So I will use this way of saying it's small, but you can do it in the usual way. So if you have a collection of functions and they're equally concentrated, then you would say, if you give me an epsilon and I have a bunch of functions, then I would have the same plateau function as the disposition, a compactly supported function, non-negative if you want, which is reproducing it in a uniform way. Now, if you think, for example, of the Dirac functions or so, I mean the Dirac sequence, you're compressing the Gauss function, and well, maybe sometimes you say they have to be supported, or if you take a Gauss function, the tails are getting even smaller and smaller. Now, you could say these are tight functions in the set C0, because they are uniformly concentrated in exactly this way. The tails are tiny. In my terminology, I try to avoid this example, for example, because very rarely I need unbounded sets, and clearly these Gauss functions blow up to infinity, unbounded sets which are uniformly concentrated. You can say I'm restricting my possible domain of terminology or so, but I found it more convenient to restrict the terminology, but that's kind of my decision, to bounded sets. So a bounded set will be called tight. Sometimes I will remind you, when I talk about tightness, I mean bounded set. So yes, a collection of bump functions which are more or less in a box. And then there's a little tail outside, an epsilon strip at infinity. All the functions that you can graph, this is a tight set. Now, what is a typical example of a non-tight set? If I give you a set of translates, you have some bump function, and you move it around. Well, if you move it around in a compact interval, so shifted versions from -10 to +10, you can make a large enough box and everything will be okay. If I take the bump function and move it to infinity, so you have a function and it's going away here, is it tight? And the answer is no, because if you fix the plateau function, eventually I will be outside of the support of the plateau function, so my error compared to will be huge. So that's actually the main point. We will later on discuss the concept of weak star convergence of measures. So you're applying measures to test functions or so, and there are two ways of things going to zero, so to say. Yeah.
Are you saying it's a compact set of functions?
No, I'm not saying it's a compact set. It's there is a criterion which we may come later, not today, where you say if it's yeah, maybe I can give a comment on this in a moment. Yeah, well, that's a good question. So just to say, if you have a sequence of functions, they can melt to zero by getting small. That's quite clear. Then they are norm convergent to zero. Then a sequence which is convergent to zero will, of course, be a tight sequence because. Yeah? Oh, sorry. Yeah, no, that was. No, they're either. So sorry. That's a mix-up. Sorry, I have to correct that. Now I understand why you're asking this question. So no, I should write a plateau function. I was writing P, but I was thinking that that's a mix-up, of course. But the story was, I'm telling you now, everything is concentrated in that compact set. That's the support of the plateau function. So you can have two versions, and I spell it out in words. Either you're saying there exists some plateau function, or you can say any function, but plateau functions are reasonable, with compact support, such that if you cut with the plateau function, you have a good approximation, because the main part is reproduced and the rest is small. The alternative would be there's a compact set such that if you measure, then you would put the indicator function of the compact set. So roughly speaking, you would have a sharp edge and you would have a box function, but you would write it down directly by saying, I have a compact set such that every values of all the functions in the family outside that compact set are all smaller than epsilon. So kind of that's a mix-up, and sorry for this. But
in some sense it's an approximate identity for M.
yes, yeah. So kind of if that's another will be another terminology which is not really in the literature, that the approximate identity which a priori works individually works uniformly of uniform quality. Now I was taking your question to mention that also as the question of is it meaning that the set, but I was thinking of this set, that the set M is compact, and the answer is the compact sets are exactly the ones which have this property, plus they are equicontinuous. So they are equally the same epsilon for the same delta for the same epsilon. So just to give you an idea, if somebody is having an individual function in C0, it will be tight. If you have 10 or 100,000 individual finitely many functions, you will be tight. A nice exercise is if somebody gives you a tight set and says take the closure, then it's also tight, because you can use the tightness condition with epsilon 1/2, and the other epsilon 1/2 you use to go to the closure. So yes, the closure of any tight set is tight. Anything which can be approximated by finite sets, and that's compact sets, have to be tight. Answer or question, is it enough to have tightness? And then of course you say, well, is the set of bounded functions on the unit interval, is this a compact set? And then you go to Arcela-Ascoli and say, well, no, it's compact if and only if, more or less, you can conclude from pointwise convergence to uniform convergence. And that's only if those functions are uniform quality. Because then you're saying, well, I have a very thin collection of points where I know it's a convergent, and I jump with these little delta balls to all the other points and I get universe. But we will not need this now, but it will be an important ingredient in characterizing compactness in function spaces. Now, the other thing is this concept of uniform concentration can be actually used for LP spaces, for many other spaces or so, as long as you have a reservoir of plateau functions. And again, you could say even in the Fourier algebra we could multiply with plateau functions with smooth edges. That's why I prefer the terminology instead of pointwise descriptions. And if you have measures, then you can do it in the same way. You can say now a set of measures is uniformly concentrated or tight. And again, I prefer to say a bounded set of measures is tight if you find a plateau function such that all measures in this set are okay. So if you think of a collection of deltas, you give me a sequence of delta at points xn, then tightness of course means they have to be in a compact set, because if they have a subsequence going to infinity, then I'm getting out of the support, and then I will have no possibility. I mean, the P of m will be 0 because I'm outside of the support. The delta xn will survive. The norm will be 1. So no chance to get it for any epsilon less than 1. Now, one thing that I find quite important is that to observe that the family of discretized versions of our operator are also uniformly tight. So we have a lot of these discrete versions of these things. They kind of, if you apply them, they are doing a good job, but they are concentrated in the same domain. Remember, I was giving you the indication, and I think I will prepare some plot or search some plot where this distribution function story was done. So if you have a distribution function which is concentrated, then you can think, well, I make now step functions, but I can start at some point where the distribution function is at level epsilon, and I can stop to do the whole thing where I'm at 1 minus epsilon. So there is some domain where most of the mass of this measure is concentrated, and if I introduce step functions instead of the smooth one, I will not move information quite far. So this will be quite important. So somehow the thing that I will talk about, the convergence of these discretized versions of a given measure, will be also allowing me to talk later about families of function which are having this property. So maybe as an example, we have more or less seen, and I will maybe discuss it once more in some detail, that if we have some measure and we want to do the convolution. Now slowly I'm starting to write the usual star, but still I want to mention we are at the moment we are only allowed to take a measure and the function, and the measure is a bounded measure, a functional and a star. And actually somehow I'm thinking, well, if you tell me this is your measure, we can have this flip the function, shift it around, but I rather say no, shift your m, the impulse response, and think you're having moving average. I will explain also why this flip is. Okay, so then this mu alpha would be, the index set alpha would be the set of all partitions of unity. And there are good ones which are fine and others which are not. So now we have, I'm talking, if there's a net, a bounded net of measures, and if this bounded net is uniformly concentrated, so they have very much the properties of this discretized version of this measure, then we have convergence. So I will try to explain that a little bit. Well, let's see. Maybe yeah, I will come to this maybe because I don't want to switch too much. Maybe I can give you the key observation. The key observation is the following, that if you convolve a measure, recall, let's look at the thing pointwise. So if somebody says, what is happening at the point x? So we look at mu alpha f at the point x. What we have to do is to say, well, take your function f, flip it, move it to the position x, and now you have a measure. Now, any C0 function shifted, flipped is a C0 function. So Tx of f flipped is a C0 function. To say that it's weak star convergent means, of course, that if you apply the measure now, mu alpha of this thing will go to the limit mu 0. So somehow we are already in a good situation. We can observe that the convolution products of what I had before, so I will go back to this, the convolution products will go to 0. Actually, for the case that these are the discrete measures, we're applying a discretized version of a given measure to some function, let's say Tx f flipped. Now, if we apply a discretized version of a measure to a function, what does it mean? This discretization operator and the joint operator. It means I should take the measure and apply it to the spline approximation. So I have to have this argument somewhere else, but I don't want to switch to the blackboard. I try to do it in verse now. So we have to think what happens if I take a measure and now I'm having, instead of the function, at every point another spline approximation. It's unfortunately not convolving the measure with the spline approximation, but applying the spline approximation operator to this shifted flipped version. And because the function is shifting, this is not just, I mean, this piecewise linear interpolation and shifting is of course not exactly the same. But what we can say, what was the estimate how close a function is to a piecewise linear interpolator or a spline interpolator? Do you remember the estimate? There was a key estimate. It was the oscillation function. And the oscillation function only depends on how much the function goes up and down. That would be the epsilon delta. So if I have, and that's now a bold abstract statement, a function which is a family of function which is equicontinuous, which simply means you're using the same delta for the same epsilon, even if you shift the function, if you flip it, all these shifted versions, they are equally rough or nicer. So that means if I have to prove the uniform convergence, I will have it somewhere. Uniform convergence for the case that these are the discretized measures, we only have to know that this can be moved over and we can get this result of uniform convergence for free. And I think that was one of the key issues why we can say if we understand the convolution with discrete measures, we can go to the limit and go on. It seems that in that preparation I was doing, I was more focusing to go now finally to the definition of what the convolution of bounded measures is. So we have right now, the last statement was, whether you're talking about invariant systems or whether you're talking about measures, that's the same, because for every measure of some norm, there is an operator commuting with translation of the same norm, and we can go back and forth, and we have the rule, and the mapping is well understood. Now, we know, of course, that this algebra of operators, we don't need the commutativity, we have it already, but that this algebra is having a composition law. We just compose operators. It's a harmless exercise. If somebody is giving you two operators commuting with translation, then the composition is also translating. First you shift through the first one, then the second one, the composite operator. Another quite important observation is if you do composition of operators, it's clearly associative. Usually I'm saying in Austria, if I take the train from Vienna to St. Pölten, which is a little town, and from St. Pölten to Linz, and then to Salzburg, I can say I took the train from Vienna to Linz through St. Pölten, and then I was continuing to Salzburg. Or I can say, no, I took the train from Vienna to St. Pölten, and then I took the train from St. Pölten through Linz to Salzburg. You will say, well, he took the train from Vienna over St. Pölten, Linz to Salzburg, which is the associate law for composition. Now, we have a very similar situation already in the case of linear mappings from Rn to Rm to Rk or so. We know that if you choose the standard basis, then we can describe every linear mapping by a matrix representation. Of course, it's very good for young students to check that matrix multiplication is associative. And maybe they even get to know at a very early stage that matrix multiplication is representing linear mappings, because that might be too abstract in applied courses or so. But I tried in my course to essentially to make that big effort of saying, well, you know, it's about linearity, and because composition of linear mappings is linear and associative and so on, if you describe the first step by a matrix and the second step by a matrix and the compound matrix by a matrix, associativity comes for free. And I think it's good to do it both ways. So you have seen already in the beginning, in the preparation part of the course, that convolution of integrable function is associative. And you have seen there is integration theory going on into it. It's Fubini and interchange of integrals or so. But it's okay. We will come back to this point by saying, well, integrable functions are special measures. We would say absolutely continuous measures. Convolution of measures is introduced in an abstract way, but it is reflected in what you do. So we're really doing more or less the same thing, but from a completely different angle. So what is the idea? I have two Banach spaces. And one, the operators, has an extra structure. You can multiply. And then you just say, well, I transfer the structure over to this. And because I have not really formally introduced the Fourier algebra, I would like to tell you this is exactly the same idea. We have L1, that if you know L1, I can say you can look at the Fourier algebra. You can look at all the Fourier transforms of L1 functions. You verify, as we have done, that this is a Banach algebra. It's closed, you estimate it, the L1 norm and so. And you have an injectivity. So there's an injective mapping of the nice Banach algebra L1 with convolution to a collection of continuous functions which are inside C0. Now, a priori, this is a set. But because of the convolution theorem, I can say, well, if I take pointwise multiplication and I take the norm with me, so kind of all the interesting structure, the Fourier algebra is a Banach algebra with pointwise multiplications. And the Gauss function compressed are an approximate unit. So I take the image, which is the Gauss function stretched, is an approximate unit with respect to this fancy norm. I don't have to care too much what the norm is in this case, but I transfer structure. So in this case, the operators are nice algebra. They're even a commutative algebra. And therefore, I'm going to the measures, which are now getting the structure of an algebra. Now, before going to this, I realized that I have in the course notes, in the lecture notes, I was doing it earlier, but then I had to talk a lot about measures before coming to that main interesting point that we have now. I have not really spelled out why is it really the same to do a convolution of a function with a Dirac measure or whether I do a shift. So just to step back, dual measures are bounded linear functionals. Delta x is the name of the point evaluation operator. I think nobody has a trouble to understand that this is clearly a functional. It's linear. If you pick the value of the functions, it's the addition of functions why it's linear. And it's of norm 1, which simply means if somebody gives you the delta of x, so the function value, absolute value, can you estimate f of x, absolute value, by the norm? And clearly the super over all values is dominating the individual value. This tells you that the delta x has a norm at most 1. Is it equal to 1? Well, this doesn't mean that every function has to have, with maximum 1 has to have this, but there are some functions of norm 1 which are okay, or at least close to it. But of course, you take any plateau function which is 1 near that point x, it was maximum 1. So there are some functions which have maximum 1 and have point value 1. So therefore, the delta x, the measure delta x, has norm 1. I would say it's a nice and interesting example that if you take delta at 0 or delta at x and delta at y negative, so the difference of two deltas at different positions to compute the norm. Actually, this is 2, because you can find a function which is continuous, taking the value plus 1 here, going down minus 1 here. So if you apply delta of x minus delta y to such a function, you get plus 1 minus minus 1, which is 2. But the function can be within a strip of width 1. I'm sorry, I should have put this in this position. So, okay, so we understand the deltas are, I would call them the most simple objects. The finite discrete measures are just the finite sums of deltas, and they will be understood easily now. But we have a formal procedure to go from measures to operators. So what is the abstract convolution, or I could have written, what is the convolution operator applied to the function f, to take the original terminology. And the rule is convolution operators are take that functional applied to the function f flipped, shifted to the position, set equals, sorry, yeah. No, it's right, sorry. Delta x is a fixed point where you want to have the action, but delta x convolved with f is a function which has arguments. So I choose an arbitrary argument, and that argument is coming here, of course. So that's correct. So we have to switch the role of flip and shift operator. And of course, if you flip a function and then you shift it, it's the same as shifting it first in the negative direction and then flipping it. Maybe you can make the argument a little bit shorter, but this of course means now that the point was then this is one function, and I want to evaluate one function. So I have to evaluate the function with the name t of minus z f flipped at the point x, and the flip is appearing by the minus here. So this is okay here. Now what is this? It means instead of evaluating the function f at minus x, before writing the full argument, I have to write minus what is in the index here. And to see how it appears, I wrote minus the minus set, which is here, which is clearly, if you write it out, plus set minus x, which is the shifted version txf at set. So for every function f, this object which is defined abstractly and this object which is concrete have the same value at every set, so they're equal. For every set means this operator convolve with Dirac measure or apply the shift operator as we have defined it is correct. And that's the point where you see what the advantages of having the flip. if we wouldn't have flipped, you would write more or less the same. What is the moving average with delta at +1? Let's try it in this way. So I have a function, and I want to know at this position, at I don't know x equals 5, what is the value? And then I have to say I'm sitting here. I have to have my delta 1 here. It picks out this value, and it moves that value and puts it here. And then you see that suddenly I'm pulling back to the left. Also, I was using delta at +1. So that's not convenient, I would say. I think you could argue that this multiplication rule, I mean, we have, I don't want to write it down, of course, nice compatibility between flip and convolution. So if you convolve two functions, you can flip them individually, or you convolve them and then flip this. It's essentially a dilation with -1 or so. So I could also say the moving averages have a convolution structure, but then the match between shift operator and deltas would not be so nice, and there are many other reasons why this is okay. Now, big benefit, so this was now done in great detail. Big benefit of this is that because convolution operators commute, also the convolution among the Dirac measures is commuting, because delta of x convolved with delta of y means compose t of x with t of y. And for any locally compact abelian group, these translation operators commute, and you will have the sum which is not depending on the order, and you can rewrite in the opposite order. And that means if you have any finite measures or limit of finite measures, they would commute. And that's now another thing which I don't want to, or didn't want to discuss too much now, but we can go into details later, is that also the composition law, there's a little bit more playing with epsilon. Also, the composition law could be reduced to this understanding. I mean, you could say we know, or we define convolution of Dirac measures in the usual way. And then we would, when by linear combination, we know how to convolve finite discrete measures. And now when you want to know what is the convolution product of two measures, then I say it's the limit of discretizing the first one and discretizing the second one. But if you don't have enough background, it's hard to prove that this is a meaningful definition. But this is really, so to say, assume you have knowledge about the very fine histogram of the first measure and the second one, convolve them as discrete measures. And that's a sum of deltas, and that should be quite easy. So kind of at some other point, I will explain to you why the convolution of discrete measures, so to say convolution on the integers, or in the finite case even on the unit roots of order, is just multiplication of polynomials. So this is really what you have learned at school, multiplying out numbers, writing them, sorting them according, and then asking what is in the product polynomial the factor of x to the 7th power, and you collect all the pairs which add up with 2nd power and 5th power and 3rd power and 4th power, and that's what convolution is in a way. But this is a slightly different way of understanding it. Yes. So this is something where I would say if you want to do a proof on your own, it's plausible that when you change two things, that you shouldn't change that at once. You add some term, maybe deep psi mu1 convolved with mu2 plus minus, and then you have two pieces or so. And then it's important, of course, that all the measures that we consider, all these guys, they are uniformly bounded. They're all not larger than the measure as in the norm sense. So when you let them act, all these operators are uniformly concentrated. And the same is true for these guys here. And I will probably next week show you a theorem which is really an abstract version of this. And it's saying, I just spell it out. You have a collection of bounded operators which, if you look at these operators, they are weak star convergent, strongly convergent on the operators. Applied to the individual function, they are convergent. And if you are having these with the same property, also bounded or so, then you can compose it, and you can, and listen carefully, you can interchange the order of the limits. You cannot interchange the operators, but you can decide, well, I would like to first take the limit here. Limit would be convolved with mu2, and then you can go to this. Or you can say, first I go to this, leaving the partition here fixed. Actually, you can take the pairs with the index set with pairs, and you can say, whenever you have two different partitions of unity even, if both of them are fine, and if you know what your f is, the whole convolution product will be, of this discrete convolution, will be close to the original one. Another point, of course, that I should mention is, I was mentioning in the discussion yesterday, I think, that one of the ideas how that this discretization could happen came from studying as a student the book of my advisor Hans Reiter. If you look in the first chapter, I think he explains also what convolution is in L1, and at one point he shows that if you convolve an L1 function with another L1 function, you can approximate it by a collection of translates. And what he is doing, he is saying, well, you have to decompose the support. Think of this measure as a function. You have to support in little pieces. So he's talking about a fine decomposition of the domain. I would say, well, take measurable functions with support sitting in delta balls. And then he would say, take the mass, the integral, the area of these little balls, and take a shift parameter out of the center of these balls or somewhere out of the ball, and use the continuity of the shift that we also have seen in the L1 norm. And that's exactly more or less a concrete case of this theorem, but for the L1 norm. We will see here we have uniform convergence because f is in uniform sense. If you have it in LP, it would be the same, but this is something we have to develop next week only. So just again, orientation, and with all my pictures, we have seen that kind of this is now mixing, so to say, the normal world where people use LP spaces and so with the approach that I have taken. I have talked C0, and we have now the dual space with convolution structure, and I use MB. I mean, this is also my simple text code for bounded measures, as something which is a little bit larger than L1. So the L1 symbol was something like this caret. And Riemann-Lebesgue was saying if I rotate it by 90 degrees, this one would be inside C0. But L inf is, of course, meaning L infinity. So I have now objects which I have not used so far. But it's quite clear that L infinity is containing, with the sup norm, the bounded continuous function, is containing uniformly bounded continuous functions, is containing C0. So we have 4 layers of functions all having the same norm. It's actually will be a prototype maybe later on, or at least for further studies, of spaces where you can say, well, if you have a given norm, what is the smallest space? And normally the smallest space is the closure of the test functions in that norm. So yes, it's true, the closure of the Schwartz space with respect to the sup norm is C0. Question, is this a dual space? And the answer is more or less, I have a way of explaining it, is the L infinity space. C0 is not a dual space, but you have a dual space with the sup norm, and that's L infinity. On the other hand, the situation is a little bit more simple. You can take the bounded measures. We will see that you can take ordinary functions, interpret them as measures. You make a test function, an integrable function, to define a functional on C0, just by integration. So it's a regular distribution, so to say. And then you can say, how can you recognize L1 functions within the bounded measures? And the answer is, they are the ones which in the L1 norm or in the measure norm can be approximated here. We have seen one thing, that the measures are concentrated on compact sets more or less. So there is not big problem to have concentration. So what is lacking is smoothness. And smoothness comes from the continuous shift. So in the case of bounded measures as the big space, bounded measures are a dual space, the functions which are continuous shift invariant are also continuous shift invariant and continuous and locally concentrated, and that turns out to be the same as in the closure of this. So there's no difference. Here you have the closure of the test functions are C0. The functions which are continuous shifting are the larger space of uniformly bounded continuous functions. So pure frequencies are in the upper level and not in the lower level. So and now I would like to mention that the L1 norm, L infinity norm are kind of dual to each other. Where are the dualities? The small guy, with respect to the sup norm, which is C0, is having MB, the big guy, as the dual space. The small guy in the L1 norm sense is L1, as the big guy in the duality sense. So I have a kind of theory where you, instead of taking duality, you take a duality in the distributional sense. So you're saying, okay, we start, how can I get the, my claim is, in that theory is a paper of mine from 84 or so, I think. As a special case, I can tell it quickly now. You can say, L infinity is a dual space. How can I get the dual space? Well, I take in the space the closure of the test function in my space. I get to C0. I don't take the dual of L infinity because the space is too big and the dual would not be a space of distributions. It would not be possible to define supports or so. That's why I first go to the closure of the test functions. Okay, so now we are in the bounded measures. I could go on and take the dual of the measure spaces. Some people are studying it, but it's a very difficult object or so. And I'm saying, no, I don't want to have an object which is not a space of distributions in some sense. Which doesn't have support again. I take the closure in the bounded measures of L1. And then I take the dual. And then I'm back here. And you can play the game from the other side and say, bounded measures are a dual space. But how can I get the dual space? Well, take the closure of the test functions in MB, which is L1. Then you take the dual of this, which is L infinity, take the closure of the test function in the space. Now we are in the dual. So this, before taking a dual space, take the closure of the test function, applied twice, is of course a modification of this question of reflexivity. Reflexivity, you are asking, is the embedding of the space in the bidual space a natural embedding? And so we are saying space of the dual space, bidual space. And I'm saying, I would like to stay within distributions. Therefore, before taking dual space, I take the closure of the test functions. And it's a bit similar if you would maybe if you have a reflexive space like LP, everything would be collapsing. You would have a symbol for LP, P between 1 and infinity, and you would have another symbol for Q. And there are dual spaces, and their test functions are dense, and there you don't see this splitting of the phenomena. So just I wanted to mention this. Okay. Maybe because I have already talked about L1, we should think a little bit. I mean, I don't want to use it for the structure of my presentation altogether, but I would like to mention, of course, how we can understand L1 as a part of the bounded measure. And so actually it's enough to let the integrable functions act on, for example, on the bounded functions. And you can do this by the integral. Yeah, I think I have not prepared this in this note, so maybe I should go to the lecture notes now. Okay. Sorry, I have to run. Hopefully I don't crash in. what the latest version can do. So there are two things which I would like to introduce to you now. Maybe I skip this L1 stuff. One is the fact that you can integrate also with respect to, apply your measure to bounded continuous functions. That's something that we will need because we want to define the Fourier transform or the Fourier still test transform, if you want, so of bounded measures. So I will say, what is mu hat, the Fourier transform at the point S, and I will say, apply the measure to the pure frequency chi conjugate, so the negative frequency or so. So how can I apply this? Maybe I try to see if I can find that quickly. Yeah. My problem is I should have looked it up. Yeah, maybe can amplify this here. So what I have discussed in words was exactly this proposition. So for every bounded measure, if you apply it to an individual function, so then the action as a convolution operator goes to the convolution of the measure, which, as I pointed out, of course, if the partitions of unity are getting finer and finer, which of course has to do with the fact that you can translate the manipulation on the measure by the manipulation on this. Here you have some comments on this, but that's kind of maybe for quiet reading then. Yeah, here you see the key step in this argument which I was making in words. Oh, no, this is the warning. It's not the same to shift the spline approximation in this way or to take the spline operator applied to this thing, but that doesn't matter because in terms of errors there's a uniform quality, so that's maybe the thing. So I should try to find the place where I have now. Yeah, maybe a small comment which is not worthwhile long discussions or so. You can define the flip of a measure by saying the flip operator applied to measure is the same as applying the measure to the flipped function. This is, for example, justified by the fact that it coincides with the idea that delta x should be replaced by delta minus x. And because it's working in this way, then you can say, well, what happens if I convolve with the flipped measure? And then there are some identities saying, well, you could also do the same by flipping the function first and then convolving with the measure, and the result is flipped again. Now, the flip before and after the convolution with the measure do not change the norm of the operator. So the convolution operator with the measure has the same norm, and of course the measure and the flipped measure has the same property. This is somehow a very harmless, very trivial property or so, but as we can learn from the general theory of Banach algebras, to have an involution, and that's kind of part of the involution in an algebra, is allowing a lot of good properties or so. So the involution is harmless, but it's quite helpful to have it. Yeah, so here you have the rule, of course, that if you flip two functions in spirit, you can do many of the things that I'm doing here also for non-commutative groups, and then it's good to change the order because we are on the abelian group RD. That's not a problem here. Yeah. Maybe I come to this point because I have it now on the screen, and that's the question of, can we extend the operators that we have to the measures? And one idea is that we can say we have ordinary functions, And there are two ways of looking at them now. We can look at them as ordinary functions, so they are part of C0. So we can dilate them and all these things. But we can also make functionals out of them. So we use them to integrate against these things. That was what I was not showing very well until now. But I think you have done it already. So the idea is to have a way of doing it in such a way that it doesn't matter, we have consistency. Or that if you say, well, how should I define the translation operator on a Dirac? Well, we have an internal multiplication that is shift by x is convolved with delta x. We can multiply in the algebra with delta x, so it should be the same. And in the same way, how should I dilate a function or compress it or so? I would say take a function, move it here, and then you approximate better and better and move it in the same way. So all the operators that we have, that's kind of functional analytic tricks which make the operators which we have already more general and apply them to the more general situation. So the first question is, what could be the STM of f? So what I call the stretching operator or the mass preserving measure applied to some function f. And the answer is I will do the measure and apply it to the dilated version in my terminology of f. And I hope I have then something written there. Yeah, I can do the same thing with changing the roles of stretching or so. And then damn. I'm too much in the notes now. Probably I should use a blackboard now, but I will tell you just this idea of what happens when you apply the st-rho operator, now the extended st-rho operator, to a delta. So assume you have delta at 3 and your stretching parameter rho equals 2. Then somehow I'm telling you, if it was a function, I would take the function, stretch it, move everything from the support where I'm now to the support times 2. But I would try to make sure that the area, the total mass, is preserved. Now I have a point mass, so to say. It's concentrated at the point 3. And it's a single point mass, and I would like to move it by changing the support from 3 to 2 times 3. So you're getting a position 6. But the mass should be the same, that would be a delta. So in this way, you will get that the st-rho operator applied to a delta will be just moving the points from their positions. The other one is the d-rho operator. Here you see the d-rho. Here you can see it. The d-rho operator is now the adjoint of st-rho operator on the functions, but the st-rho operator would rescale the functions. So you're having an extra effect. You're moving the mass, but you're multiplying it. And I think what I have here is the illustration of this effect. I mean, the place where I'm explaining it is not the best one, but maybe I can do it better now with this on the screen. If somebody is giving you a Dirac comp, I know that this is not a bounded measure, but let's assume you have finitely many Diracs or so. And you apply the stretching operator. Let's say it's a standard lattice, unit lattice from minus 10 to plus 10. You have 21 Diracs sitting at those 21 integer points. Now I say I'm applying the stretching operator with rho equals 2. Then each of these Dirac measures will move from position x to position 2x. So we will have Dirac sitting at minus 20, minus 18, 0, 2, 4, and so on. What if I replace 2 by 5 or 10 or 700 or let rho go to infinity? What would you say what happens? So these Diracs would move away. So if I'm a test function living somewhere over the table here, and here's 0, and these deltas move away, only the 0 guy would be remaining. So the weak star limit of this finite measure with everything moving to infinity would be just the 0 part. So delta 0 is remaining. All the others would move to infinity. Even if you have, I don't know, 100 times delta at minus epsilon, if you stretch it far enough, it would go to 0. Well, if I'm not a test function, I would be a C0 function, and it would be very small. So the effect of the rest would still fade away very small, or very fine or so. But now the interesting thing is, what is the opposite thing? If you apply the ST rho operator for rho 1/2 or so, you would sample from -5 to +5 at step which 1/2. You're getting more and more. So at the limit, what would you get? So think of rho very small. You have 21 Diracs, because it was always 21 Diracs, sitting almost at 0. Not exactly, but almost. So if you apply it to an F, you would get in the limit, what is the limit? It would be 21 times the value at 0. So if I would have an infinite Dirac comb, it would infinitely times Dirac at 0. So that's not a very good thing. However, what I could do is, I could say, well, kind of I have a function which is living on -1/2 plus 1/2. And I have my Dirac comb compressed, but I have the rescaling. Now suddenly, the distance is 1/10, but I scale everything with 1/10. And I'm saying, okay, my suggestion is look at sampling value here at distance 1/10 and adding them up over the support, multiplying everything with 1/10. Maybe then I take a few more and I take 1/30, and I take sampling at 1/30, rescale with 1/30. What I'm talking now? Yeah, but you know this, what I'm talking. It's a weighted sum with amplitudes which are shrinking with the size of the sampling. It's a Riemannian sum. So what we will see later on, that's really far-fetched now, this Dirac comb will have a Fourier transform in a distributional way. And its Fourier transform will be well defined. And whereas if we take the Dirac comb and stretch it ST rho operator, it goes to the delta. So what do you expect that the Fourier transform side is doing? Well, instead of the ST rho operator, you have the D rho operator, which means you make the points dance and dance, but you keep not now the mass of the individual points constant, but you try to keep the local mass distribution, the total mass constant. So it's like you would concentrate constant 1, and you also have 1 in every interval. So now we have the total sum in an interval of fixed length is concentrated. Well, we're doing Riemannian sums. So these Riemannian sums converge to the integral of the Fourier transform on the Fourier transform side. And the integral is, of course, making the function constant 1 into a distribution. So integrating again constant 1 is the integral of a function. So somehow we will see if we have then enough terminology in the distribution sense, then we will be able to say that something which is a weak star limit of delta will on the Fourier transform side have a limit equal to 1. And that will be quite useful also. So I'm sorry, but I think I better use the time now before jumping too much to recall some concept which I wanted to do anyway, which is the concept of a Banach module. So some of the things that we have done so far can be nicely and conveniently explained by the terminology of Banach modules. And so I want to explain to you what a Banach module is. We have understood, I think, now what Banach algebras are, and we will mostly be interested in commutative Banach algebra in this course, and those which have no unit but have a bounded approximate units. These would be really the interesting objects. In functional analysis, you're saying, okay, we have only Banach spaces. Only Banach spaces means these are vector spaces with a norm which is complete. So the scalars are, of course, working here. Well, actually, very often we say, well, Then we look at operators on these Banach spaces. So somehow the meaning is with every Banach space we have all the operators. We're doing linear algebra, we're having column vectors of length n. We say this is Rn. But we're studying the linear mappings from Rn to Rn, and suddenly we're jumping into matrix analysis or so. The aspect that's coming in, I would say, when we do harmonic analysis, it's good to know about function spaces. They're infinite dimensional, therefore we need these duality tricks and all these things. But we also concentrate only not on all the possible operators, but we are restricting our attention to certain operators. So we just have seen the convolution operators are of particular interest to us. There are many other operators which make a huge non-commutative space of algebras, but to say, well, out of this huge possibility of all operators, we choose particular operators which have to do very often with group actions. We have seen we have the shift operators, and we have used them to get all the convolution operators. If you take the Fourier image of this, we say we have the modulation operators. You can have a linear combination of modulation operators. That's a multiplication operator with a trigonometric polynomial. And if I just translate my deep psi convergence story into the Fourier image, you would say, oh, he is multiplying with trigonometric polynomials, but at the end he is getting the action of an FL1 function. So he can multiply with a Fourier algebra element and think that this is practically a limit of modulation operators. And you could do the same thing with dilation in 2D. You can do rotations, and the larger the group is, the more groups can act on various spaces. And what I'm really trying to tell you, that will be, I can do it only probably on Monday, is the integrated group action. So the convolution on measures can be not only done on C0, but on many, many other spaces. So this is kind of the universal model for getting from individual action of group elements to the action of L1, or I would say better, all the bounded measures. So to make it short, there is a well-established terminology of Banach modules, which for me is a compact way of saying sometimes it's good to say we have a Banach space, but we draw particular attention to some Banach algebra of operators. So the terminology emphasizes more the aspect that you say, I have a Banach algebra, that's interesting to me. I would say I have L1. And now we have seen L1 is not just an internal multiplication, but we can let L1 act on LP. We've seen in the very nice proof how you can do this action. I have shown that the measures act on C0. I have already implicitly used that C0 functions can be multiplied on the measures. So there are many module actions already in the game, and we make it more formal now. So what you need to define a Banach module is more or less something that replaces or adds to the scalar action another algebra of operators. So a Banach space is a Banach module or a Banach algebra A, and this algebra has some internal multiplication. If one has a multiplication, meaning a bilinear mapping, so you can add in the algebra term, you can add in the second term from A to B with the corresponding estimate. So if you have the action of the algebra element, you can estimate that action by the norm of the algebra times the norm of the element on which the action takes place. Now, there are many, many examples of this. One example would be you could take an algebra itself. Every algebra is a Banach module over itself, and just replace B by A, then it's no problem. A prototypical thing would be you can take Cn and take all the matrices. Then you would say, oh, the A norm is now the operator norm, what I use with the triple bar. Matrices with the operator norm are of course closed under composition or so. And now we have, again in MATLAB, it's more or less the same star or so, but we should distinguish between matrix vector multiplication and internal matrix multiplication. So we can say, if we have a matrix acting on a column vector, we can also have another matrix. So in MATLAB you would probably write, if to choose the same symbols, maybe matrix A1 with A2 with B. And MATLAB, an interpreting language, would read it as A has to be multiplied with A2. Oh, I have to do matrix multiplication. Now I have the product matrix and I apply it to the vector. I tell you on the side now a trick to speed up the process. I say make a bracket around A2 with the vector. And then you have A1 applies to, okay, first I have to do the action of the matrix on the vector, matrix vector multiplication. This costs me n squared multiplication. N scalar products means n squared multiplications. Now comes the square matrix A1. I apply it, so I have once more n squared multiplications. So by putting a bracket, I have speeded up the code a little bit because now I need 2 n squared multiplication. MATLAB, at least for a long time, was in that point, it's very smart, in that point not so smart, because it was saying I have to do matrix multiplication. It's doing n squared new terms for the product matrix, which means n third power multiplications. And now we have the product matrix and do it here. What you see is that even in a very practical situation, this internal and external is not the same, but because we are using this star, we are not surprised that associativity is taking place. So in MATLAB you can write triple expressions even if the vector matrix multiplication and the matrix multiplication are only defined bilinearly. Due to the associativity, it's no problem. And that's actually one of the things that I think when you have a good calculus, that's a kind of a general side remark, a good calculus, and that has to do now with the use of the operators, the interpretation of functions as distributions or so. If you look more carefully, some of the very nice and compact proofs are really something that you're starting with something, then you're putting brackets maybe without observing it, and you have triple expression and say, now you see, this is nice because it's a product of something, and this is nice secretly using associative law. Then you're saying, well, originally this was a function which was nasty, but now we have smoothed it. Now instead of having a distribution, which it was originally applying to a test function, now it's an L2 function. This is another L2 function, so we reinterpret this scalar product in a different way. So all these things have to be justified, but it will be justified by the setup. So kind of not every user at every step has to check, am I allowed to do it? But the symbols should be made such that everything that the symbols allow you is solid, and everything that you are not allowed to do, like taking a delta square or so, should be also not be part of this thing. And that's a point where I would say sometimes engineers are in the danger of getting to misleading statements because they are too often told, well, you don't have to understand these, we just play around with the symbols, we use these things, and then it's not. So I will try to help in this respect. Okay, so once more, for me, and the correct terminology, actually, to come back to the slides, would be to say a left module, because, well, not so much because I have put things on the left-hand side, but because the associativity law was coming from the left-hand side. You can just take another story. You can take 3x3 matrix acting on vectors, but what I call the bullet could be take the transpose of your matrix and multiply with the transpose from this side. Then everybody would understand that if you multiply with the transpose, you have the opposite law of associativity or so. So you could say, well, I have to transpose everything, then I would actually not have column vectors. I would apply a row vector, and I would apply with my matrix here. That would be, from my side, the more efficient way of looking at these things. But you can also have the other idea to say a right module is a module where you still write the symbols on the left-hand side, but the associativity is going in the other way around. If your Banach algebra is commutative, you don't have to worry about the order, and that will apply in most of our cases or so. But I must say that this positioning of the symbols is quite good. Now, just to use the rest of the time to introduce a little bit of terminology. A Banach ideal, this is not completely widely established.
We are using C naught and M as also in the module structure, right?
Yeah, so we can put them in a module setting now. Then yeah.
In fact, two Banach algebras, one is the dual of the other. We can think in that way.
Yes, that's coming up. Thank you. I want to do exactly the abstract viewpoint, and then we are back to the concrete case. So terminology, a Banach ideal is of course something which is not just an outside action, but an inside action. I mean, this was really something I learned very early. I think Professor Rada also know this. The Siegel algebras are these Banach modules with respect to convolutions which are sitting inside the algebra or so. Whereas LP on the real line is a typical Banach module, is sitting outside. I mean, not outside, it's not sitting inside. Part of L1, LP are inside LP, but that's kind of where you use this Banach module terminology. Yeah, and here you have this comment in the definition 25. An abstract Siegel algebra is if you have a Banach algebra and you are having a subalgebra which is an ideal and which is dense, and there is also a notion of essentiality. I will, at the moment I will try to make it short. I will say if the Banach algebra has approximate identities, and all the examples that we discuss have this property, then an essential module means take the approximate identity from the algebra, and actually I would say here is a typo, that should be a bullet, because I'm really saying these approximate identities are in the algebra. So maybe the Gauss-Dirac function is a good thing in L1, but now you start to apply it to LP, and you want to know, is this going to 0? So an essential module is one where the action of those approximate units is what you expect. Now, again, we can take the example of LP spaces. You can say LP spaces, all of them have the property that shift is continuous, and that buys you that they are all essential modules if P is less than infinity. And then you can ask, well, what happens if you have L infinity? Well, then the essential part is exactly the part where this is okay, and you have to throw away the other ones. And it's not so difficult to find out that these are exactly the functions which have continuous shift. And the continuous shift buys you uniform continuity, not just within the continuous bounded functions, but even within L infinity. So L infinity is not an essential module. It's trivial that it's a module. L1 with L infinity is giving you bounded continuous, even uniformly continuous functions. But the essential part is really strictly less. So another way, and that was my introduction, a Banach module is if you have a Banach algebra, a Banach module over a given Banach algebra is more or less the same that the Banach algebra is sitting inside the operators. And there are usually some precautions in an abstract definition. Say, I can make every Banach space into a Banach module over every Banach algebra. I take the action, every element is acting as 0 operator. And you say, oh, okay, come on, that's nonsense. Yeah. So that's why very often you want to have an injective, so that if an element of the algebra is acting in a trivial way, you would hope, I mean, it's trivial on all the elements, then it should be the 0 element. And there's a very easy trick. If you have a situation where this is not the case, then all the elements which act trivial on all the elements, they're an ideal, and then you factor out and you get a kind of a true action, a good representation. So I think I would like to just mention this, what Professor Rada was indicating. If you have a dual space, where is it? Here it's correct with the bullet, and it repeats. Yeah, here. This is something I have inserted only very recently, also because of our concrete example or so. If somebody is giving you a Banach algebra acting on a Banach space or a Banach module or so, then we have a lot of operators and they're closed under composition. each of these operators has a transpose, and this operator acts on the dual space. Therefore, you can say, well, maybe I can take my dual space and can take the dual operators, or I should say transpose operators. So it's duality in the sense of Banach spaces or so. And the way that is used quite often is you say now there's a new action on the elements of the dual space. So I'm thinking of a distribution or a measure. So A applied to sigma at B is sigma, and you apply this again should be a bullet, the A to the underlying element B. Then I realized it's actually better. Okay, sorry. And then if you follow up by the law for transpose operators, you have this left, from the left action you get the right action. So you have A2 with A1 is the same as A1 with A2. That should be internal multiplication. Again, I have to correct it, applied here.
You get the Aaron's product, right?
I'm not sure. Well, if you, the Arens is one, I think it's for the bidual. So kind of that's another interesting story which I will not follow up. You could say every algebra is a module over itself. Therefore, the dual space is a module over the original algebra. Therefore, the bidual is a module, but you can even try to make a multiplication within the bidual space. And that's the Arens product. I mean, I think that's more or less. Now, what you see here is this law is a little bit unintuitive. And so I think I was typing in, just the alternative, which I'm trying to follow now, actually, even in the concrete writing. So we were saying, I was cutting the measure into pieces by taking, usually it's like scalar multiplication, you would say psi I with mu. But if you write psi with mu or mu with psi I, that's not a big difference. But if you think, well, if I write mu multiplied with psi I applied to a function f, now the bracket is around the f, is like mu applied to psi I times f. It's just moving the bracket, or actually saying the expression mu with psi with f is meaningful, either as mu with psi as the action, the modified action, or the multiplied function. So I can multiply, go on both sides. Do this in an abstract way would be the following. No, I think I've moved away from this. Yeah, here. This would be an alternative definition. I would say because I expect a right module coming out of the left module because of transpose mappings have a different order, I have a new bullet, so to say, a new action of my old algebra on the dual space of the original space. And that would be put on the right. And then I would say it's what I had before. This is the same as before up to the typo. And but then the order is quite clear, because if a sigma is coming with an algebra element, I know I'm in the dual space, and I had only an action of the algebra on the space. So it must be a new bullet, so to say. But if I move it on this space, it's the old bullet. So this should be a bullet. I have to do some corrections on the coder. So now maybe I should stop now. But essentially what we will do is what we have done with the multiplication of measures and convolution, and so that's all compatible now, and we have a lot of Banach modules already now in our story, and I will continue with that. Okay, thank you very much for now.